A 55 kilogram mass hangs from the ceiling by a single rope. Find the tension in the rope. So there's a model of our situation. What's the tension in that rope? Let's draw a free body diagram. 55 kilogram mass. We have the weight that is acting downward, which we know is equal to m, in this case m is 55, times g, which is 9.81 meters per second squared. So 55 times 9.81 is 539.6. Then we have the tension from the rope acting upwards. So let's sum the forces on this mass. If I choose upward to be positive, we have tension minus 539.6, and the sum of those forces, according to Newton's second law, should equal the mass of the object times the acceleration. Well, that object is at rest, so it's not accelerating. So that means we can very easily solve for the tension in this rope, and we're going to round it to two significant figures because our mass had two significant figures. So 540 newtons is a pretty good way to go. Maybe this mass is a chandelier or a disco ball with John Travolta doing a little Saturday Night Fever. Okay, we have the same mass, but now it hangs from two ropes, each having an angle of 60 degrees above the horizontal. Find the tension in each rope. There's our mass. The ropes are angled at 60 degrees above the horizontal, and we want to find the tension in each rope. Now, to do this, we're going to have to make a couple of assumptions. Okay, we're going to assume that the ropes are the same material, same thickness, and that they are distributed evenly with regard to the mass, so that the tensions in those two will be the same. If they were at different angles, that would be one thing. But here they're at the same angle, so we're just going to call the tension in each of those ropes T. So let's draw a free body diagram. There's our 55 kilogram mass. There's the weight, which is m, 55 times g, 9.81. These tensions are not directed straight up and down or straight left and right. You can see that the rope is angled somewhat up and down, but also somewhat left and right. So I need to break that tension into a horizontal or x component and a vertical or a y component. Now you can see that in the x direction, if these tensions are the same, then this leftward pulling t sub x and this rightward pulling t sub x are exactly going to cancel each other. But the ty components are going to somehow be related to this weight, 539.6 newtons. Let's sum the forces in the y direction, in the up and down direction. I'm going to call up to be positive. Notice that we've got a ty there and another ty there. That's two ty's. We have the weight acting downward. The sum of those forces, according to Newton's second law, should equal the mass of the object times the acceleration in that y direction. This mass is at rest, so the right side reduces to 0, which means that 2 times this ty component is equal to 539.6 newtons, which means if we divide both sides by 2, the ty is 269.8 newtons. But we don't want ty. We don't want the y component of the tension. We want the tension. How is the tension related to ty and this angle? You've had a little experience with sines and cosines. You know that the tension times the sine of 60 is equal to ty. So to find t, which is what we're after, we're going to take 269.8 and divide by the sine of 60, which will give us a tension in those ropes of 310 newtons, rounded to two significant figures.